Hi, and welcome to Chapter 7, Ionic Bonding. You might have heard of fool's gold. Fool's gold is actually a mineral called pyrite. It's a form of iron sulfide. And it's often mistaken for gold because it will have yellow streaks in it. It's a crystalline solid. So that leads us, since it's a compound, and it's an ionic compound, we need to know how atoms become ions. And it has to do with the number of valence electrons the atom possesses. So what are valence electrons? Valence electrons are the electrons in the highest energy level that's occupied in an element. So for instance, in something like lithium, which has an electron configuration of 1s2, 2s1. The highest energy level is 2, and the highest sublevel is the s sublevel. It has one electron in the s sublevel, so it has one valence electron. Oops. Okay. Now, if we had something in the same row, say chlorine, chlorine, 1s2, 2s2, 2p5, this would have 7 valence electrons. So this is fluorine, which becomes fluoride, and this is lithium. Okay? Now, why are these so important? This is what determines the chemical properties. Because, as I've been saying all along, how do you spell chemistry? Chemistry is spelled E-L-E-C-T-R-O-N-S, but I probably should say chemistry is spelled V-A-L-E-N-C-E, E-L-E-C-T-R-O-N-S, because it's the electrons in the outer orbitals, outer energy level, that actually interact with other atoms, and they determine the chemical properties. So how do you know, very quickly, how many valence electrons an atom has? Now we're going to only talk about representative elements to start with, because it's very easy if we look at the group number. Okay, if we look at a periodic table, we can see, I'm going to look at the group numbers going 1 through 18. You'd also have 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. But if you look at it this way, anything in group 1 has 1 valence electron, anything in group 2 has 2 valence electrons, 13, 3, 14, 4, 15, 5, 16, 6, 17, 7, and 18, 8. Okay, that is how it's set up. So just looking at the periodic table, if you can find your element, and it's one of these representative elements, which are groups 1, 2, and 13 through 18, then it's very, very easy. Okay, how can we represent these electrons? We use something called electron dot structures. So what an electron dot structure is, we use the symbol for the element to stand for the nucleus and all of the inner electrons, and then we use dots to show the valence electrons. So we would have something like, if I look at hydrogen, okay, has 1 valence electron. Now if I look at lithium, this H stands for the nucleus, and it only has 1 electron. Lithium actually has 3 electrons, so lithium now stands for the nucleus and 2 of the electrons, and then 1 dot would stand for lithium. Okay, so that's what I mean by the symbol stands for the nucleus and inner electrons. Hydrogen doesn't have any inner electrons, it only has the outer electron. Lithium does have 2 inner electrons, but it's represented by the symbol. Okay? So here's a mini periodic table that shows the different groups, and they're using the 1A through 8A convention rather than 1, 2, 13, 14, 15, 16, 17, and 18 as the group numbers. But if you look, everything in group 1A has 1 dot. Everything in 2A has 2 dots. Everything in 3A, you can see that, has 3. Okay? 4A has 4. 5A has 5. 6, 6, 7, 7, and 8, 8. And the only exception, of course, is helium, because that's row 1. There's only S electrons. S can only have 2 electrons. Okay? Just a little reminder there. Okay, so what makes an electron want to react? Well, we know the noble gases do not like to react at all. I like to think of the story about the nobles and the peasants. The nobles live in their castles and they're very snooty, and they don't want to mix with any of the peasants. So they just stay in their castles by themselves in their nice fine clothes and their put up ways. Whereas the peasants are down working hard, you know, and just getting by. And they see the nobles all dressed in these fineries and stuff, and they say, you know, I'd really like to look like those nobles. So that's like the elements. They're like the peasants. They want to look like the nobles. Okay? So what the elements do is they're able to change their outside so they can look fine when they gain or lose electrons. But inside, they're still the same elements. So they're a lot nicer than the nobles, but they look like them when they change their electron configurations. So what the elements do to become more stable, they either gain or lose electrons to get a noble gas configuration. That means they want to be as stable as the noble gases. Okay, and what we came up with was the octet rule. Elements want to have an octet, or 8 electrons, to be stable, just like the noble gases. Okay, and we call this noble gas configuration. Now, of course, I'm going to mention helium again. That's like a duo, okay? Instead of a couplet, maybe you could call it, because the highest octet energy level in helium is S1s. Okay, so the general configuration for all the other purities are NS2-NP6, as shown right here. So that's what everyone's looking for, is to have a configuration like that, or to, if you're going to be like helium, to be like that. So things, the positive ions that are after helium will lose to look like this. Hydrogen will gain to look like that, if you think about it that way. All right? Now, metals in general will lose electrons to become stable, because they don't usually have as many valence electrons. So they have less, and since they have less, it's easier for them to give them away. Non-metals tend to gain because they're kind of greedy. They have a lot already and they want more. Okay? So metals lose valence electrons to get an octet, and it will be the next lowest energy level. Non-metals tend to gain electrons or share electrons, which will be another type of bond we'll talk about in the next unit. And they get an octet that way. So it'll be in the same period as far as electron configuration. Okay, so let's look at bismuth. Let's find it in the periodic table first. So bismuth is, let's see, it's right here. Okay, there's bismuth. It's in group 15. So it's in group 15. Okay. So that means how many valence electrons does it have? Okay. So bismuth is in group 15, which we said that group 15 right, is going to be, first thing we do is draw Bi for bismuth for all the inner electrons and the nucleus. And if it's in group 15, we have 1, 2, 3, 4. Let's do it this way. Let's double up first and then put one like that. Doesn't matter where we start. We can't have any more than 2 dots per side. So if we look, see, they drew it a little differently than I did. You can either do it the way I did, keeping 2 together, or you can go around it and do the single ones. It's really up to you how you want to do it. The reason for this is if you think about the picture that they're showing you right now, oops, what they're showing you right here is these 2 electrons are in the S, and these are your 3p electrons. Just a little fact. But I would never take off if you drew it the other way. So how are cations formed? Cations are formed by losing electrons. Because the atom is neutral, it has equal numbers, so to form a cation, that means it gets positive, okay? So it has to lose electrons. Okay, so if we look here, it basically is formed when an atom loses 1 or more valence electrons. So things in group 1 will lose 1, things in group 2 will lose 2, etc. So sodium becomes Na plus 1, but we don't write the 1. Calcium ion forms a calcium cation, and let's put in the right charge. And that's 2 plus, because it loses 2. Okay? So we don't have to write the 1, but this should be 2 plus. Okay, group 1A, okay, will be plus 1. Okay, group 2A will be plus 2, and group 3 or 13 will be plus 3. So we usually have 1, plus 2, or plus 3. All right, so if we want to really figure that out, our cations are usually plus 1, plus 2, or plus 3. So we can think of that as group 1, group 2, group 3A, or group 13. Okay? So what happens to the electrons? Where do they come from? So if we're going to lose an electron, it's going to come out of the highest energy level, which is 3s1. So then, look, this is the noble gas configuration of neon. So now sodium looks like neon on the outside, but it's still sodium on the inside. And there's 1 less electron, so it has a positive charge. Okay? Notice it goes from the 3rd energy level to the next highest, so it looks like neon. So here we are again. Here's sodium. Gives up that electron. This is his electron orbital diagram, and it looks just like neon. Magnesium, okay, is in group 2A, so its electron-dot structure is this. It has 2 electrons, okay? So it's going to lose both of those electrons to get a noble gas configuration or to get a octet of electrons. So it becomes Mg2+, so it loses 2 electrons, okay? So group 1A, always plus 1, group 2A, always plus 2. Now, let's just mention the transition metal cations. Now, iron can lose 2 electrons, but it could also lose 3 valence electrons. Okay, so it can either become Fe2+ or Fe3+. And this is really pretty unique for the transition metal ions, and some of the metals that are on the far right side in the P block, okay, do the same things. The very bottom of the P block, they might have multiple oxidation numbers. And this has something to do with the fact that they often have d electrons. Well, all the transition elements have d electrons. So anything with d electrons sometimes can form multiple ions. And they don't usually necessarily have noble gas configurations. What happens is, the rule is that it loses electrons from its highest energy level. For instance, here we have an example of silver. Silver highest energy level is 5s1, so that's the one that's going to go away. Everything else stays there. So it's going to end up with a +1 oxidation number. And it would have had to lose 11 electrons to get the noble gas. It would have to lose all these Ds to get krypton's noble gas configuration. So, and to become like xenon, it would have to gain 7 more electrons because it would have to be 5s2, 5p6. So it doesn't do that. What happens is, this goes away very easily because it's a higher energy level. This then means the 4s level is totally filled, okay? As far as SPD, it has 2 s's, 6 p's, and 10 d's. This is a very stable configuration, okay? So this is usually what happens here, okay? It's sometimes the second oxidation number is a little bit more difficult to determine. Most of the transition elements have either an S1 or most of them have an S2. So most of them have an oxidation number of +2, but sometimes they can lose one of their other d electrons. Usually we don't have ionic charges much greater than +3. So here we are. This is what happened, okay, for copper. So if copper becomes copper +1, it loses this 4s electron. All right, so if we look at iron sulfide, it's going to be iron 2 with S2. So if we look at iron's configuration, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. So the most common thing would be to lose this 4s2, throw this one out, and it will look like this. This will be the Fe2 plus electron configuration. Okay, so how does cesium atom form a cation? Well, let's find it on the periodic table. Cesium is right here. It's in group 1. So it must I don't know what happened there. Okay, so it must lose 1 electron, C. Okay? So we talked about cations. Now let's talk about anions. If cations are formed by losing electrons, anions must be formed by gaining electrons. So again, gaining more valence electrons. They're a little bit greedy. They want to be like those nobles. Okay, now the only difference is the cations kept the same name. The anions changed their name and changed their ending, usually from INE to IDE. So if we look down here, chlorine becomes chloride. So it's the Cl minus. Oxygen becomes oxide because it's hard to say oxide. Oxygen becomes oxide. So if we look at this, this is the nonmetals and the 2 metalloids that will form negative ions. Notice things in group 5, 5a or 15, 16 and 17 respectively. Group 5A will be minus 3. Group 6A will be minus 2. And group 7A will be minus 1. So I'm just going to write that on top. So minus 3. So they form ions with those. That's how many valence electrons they will lose. Okay? And that will move them to the noble gas configuration over here. Whatever's here is their noble gas configuration. So it stays in the same period. Remember, the cations go to the previous period. And the reason they're not really greedy, it's just the fact that they're almost filled, so it's easier for them to get more electrons. So if we look at chlorine, it picks up one more electrons, and now it looks like the noble gas that's right next to it. Now, I didn't mention group 14, because group 14 is right in the middle. And sometimes it will gain electrons, and sometimes it will lose electrons. So they kind of have, sometimes they're like Mounds bars. Sometimes they feel like a nut, sometimes they don't. Okay, so let's look at chlorine. Chlorine will pick up another electron, and it will have the argon configuration as shown as this slide. Okay, anything in group 17 or group 7A, such as chlorine, which are all halogens, they form, as we see here, halide ions. Okay, so again, notice the change to IDE. So all the halide ions, fluoride, chloride, bromide, and iodine, have a charge of minus 1. So group 7A has minus 1. Group 6A, in which oxygen is a member, this is the noble gas configuration for oxygen, will fill in these two orbitals. So anything in group 6A will have a minus 2 electronic charge when it becomes an anion. It will look like the neon atom for oxygen. All right, so if we look at some common anions, here's our halogens, minus 1. Here's our oxygen group, oxygen and sulfur, these are very common, and then nitrogen and phosphorus will lose 3, so the endings of their names now are fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, and phosphide. So their names all change to IDE. Okay, so sulfide. Okay, let's think about this. First, let's find sulfur. Sulfide means sulfur. It's here. It's group 16. It wants to be like 18, so it needs 2 more. So sulfur will become, okay, it will gain 2 electrons. So before I go on, let's write out what it was, because we should see what its configuration is to start with. So sulfur, okay, just regular old sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So this 4 becomes a 6 when it gets 2 more electrons. Kind of different because it's a minus sign, but remember electrons are negative, so that's what happens. All right, to summarize, you've got these for your notes, some definitions. Remember, stop the video and take these in your notebook. Some more definitions. And the big idea for this unit is bonding and interactions. Atoms form positive ions, cations by losing valence electrons, and form negative ions by gaining valence electrons. That's it. See you next time.